Hi, today we'll be talking about the concepts of velocity, speed, and acceleration. In an attempt to describe motion, we said we use about 6 different quantities to do that. The first one being position, displacement, distance, velocity, speed, and acceleration. We talked about position, displacement, and distance in our previous video, where we said position refers to when an object where an object rather resides in space or in a plane. We moved on to talk about velocity. I said velocity, displacement rather, where we talked about the concept of displacement. We said it's simply when an object decides to change its position or the shortest path between 2 points. And finally, we talked about distance. If you've not seen the previous video, the link will be dropped in the description box, so do well to click on it and then get yourself up to speed. Whereas today, in an attempt to describe motion, we look at these three quantities: velocity, speed, and acceleration. We'll talk about the types as relates to motion. So the types of velocity, that is the average velocity, the instantaneous velocity. Then we'll move on to speed, average speed, and instantaneous speed. And finally, acceleration. We'll talk about the average acceleration, instantaneous acceleration. Then, on talking about the constant acceleration, or what happens when acceleration is constant, we're going to be deriving our equations of motion. Now, unlike what we did for the previous video, where we looked at displacement in 1 and 2 dimensions, for the sake of this video, we'll only be taking velocity, speed, and acceleration in 1 dimension only. And then when we look at the practical applications of motion, we'll talk about the free fall, the projectile motion, the circular motion. We look at what it means for velocity, or how we calculate velocity in 2 dimensions. All right, without wasting much time, let's delve into it. So velocity, the first velocity, we're looking at average velocity. But what is velocity itself? Remember, when we're talking about displacement, we decided, let's say we were to have a number line like this, and then I have a car at this point. So let me call this point my x initial, and then my car is moving towards this way. Let me do that properly. So this is my x initial, this is my x final, and then I have a car traveling this way till it gets here. So from the previous video, we know that the phenomenon that describes this motion is displacement, because my car has an initial position at this point where we refer to x1, and then my car ends up at this point where we refer to xf, that is my final position. Now, it is not possible for an object to change its position without the inclusion of time. What do I mean? It means when my car is here, initially it has a time, there's a t initial, and then when my car gets to this final point, it has another time, so let's say t final. Now when I decide to divide my displacement over my time, the time taken, especially alongside the part of this motion, then I'm talking about velocity. So I can simply say velocity will simply be equal to displacement over time. Note, we didn't say distance, we said displacement. So when we take displacement and then we divide by the time, then we're talking about velocity. So if we are to define velocity, we can simply say it is the rate of change of position with respect to time. The rate of change of position with respect to time. All right, that's for velocity. Now let's move on to average. When we talk about average velocity, the first thing we want to know is that we denote average velocity with this v. So let's bring that up. V, then we have a subscript a v underneath. Now, average velocity, as the name implies, when we go back to this motion, when we have the starting point, that is the starting position, we have the starting time, and then we have the final position, and then we have the final time. The velocity we can calculate as a result of this motion that has been described here is average velocity. Now, what do I mean? If I decide to take the symbolical implication of average velocity, I'll simply say, since displacement is described or denoted as delta x, then definitely if this is T1, this is Tf, that means my final time will simply be my change in T. I said final time, sorry about that. The time taken during the part of that motion will be delta T. And in physics, when we say delta over delta, then the first thing that wants to come to our mind is the slope of a line. Slope of a line, slope. So not just any line, slope of a secant, slope of a secant line. All right. Now the second thing that wants to come to our mind, aside from the slope of a line, is the rate of change, average rate of change. In physics, we have two rates of changes. The first one, average. The second one, instantaneous. Now, when we hear the word rate of change, especially as far dimensional analysis is concerned, it means you're taking a particular quantity and then you are dividing it over time. For instance, I might have a pressure flow rate, it's a rate of change. I might have a mass flow rate, also a rate of change. So what it means is basically for pressure flow rate, you take pressure, that's a quantity, you divide it over time. So when we hear the word rates of change or just rate, it means we're dividing a particular quantity divided by time. How well is the first quantity changing with respect to time? All right. Now, since displacement is measured in meters and then time measured in seconds, so definitely our velocity will be measured, or its unit will be meter per seconds. Meter per seconds. Now let's come back to our motion. When we talk about average velocity doesn't describe the specifics of our motion. For instance, again, if this were to be a car at this position and my car is being displaced towards the left, towards this position. Now, there are so many things, there are so many instances that we can derive or denote from this. For instance, the first case scenario is that my car is moving with a constant speed, leaves this point, leaves with a constant speed, and gets to this point. Also, we can say my car moves to this point here, at this particular point, it stops for a while, then continues its motion. Or we can say maybe there's a turning point somewhere. Perhaps the car leaves like this, and at this junction, it turns back to this point, then again, finally gets back to its final position. So average velocity doesn't tell us all this, because for us to calculate average velocity, we're only required to know the initial position, the initial time, the final position, and then the final time. All right. Now, let's try and expound this formula for average velocity. We say V average will be equal to x final minus x initial divided by t final minus t initial. So hope you can see this. So t final minus t initial. Remember, we said the first thing that delta over delta represents in physics is the slope of a secant line. So remember the formula to calculate the slope of the secant line. We have y2 minus y1 divided by x2 minus x1. So they look alike, they look similar. Now let's try and represent a graph this time around, an xt graph, that is a position time graph. So we can talk about what a secant line means, and then we can move on to instantaneous velocity. So let's say I have an xt graph that looks like this. So xt graph just tells us position time graph. So we're looking at how we're changing position with respect to time. So this is my t axis. This is my, so t is in seconds. So this is my x is in meters. All right, so let's assume that I have motion that goes like this. So at this point, I'm moving in this direction. Okay. Now, let me call this my x initial. Let me call this my x final. Of course, at x initial, I have a t initial here. At x final, I have a t final at this bottom place. Now, if I were to find the average velocity between these 2 points, what do I simply need to do? If this were to be a graph, of course, most of our graphs will be linear, especially when we're interpreting our xt graph or our vt graph. So we always come across linear graphs. But what if it is not linear, maybe a curve like this? So if it is a curve, the first thing you want to do is to draw a straight line that connects these 2 points, xi and xf, in such a way that it looks like this. So xi and xf. Then we find the slope of this line. So the slope of this line will simply be equal to, so we'll take any 2 points that we know. So the 2 points that we know xf, we know xi, we also know tf, we know ti. Remember the motion we constructed or that we described, where chi is moving from the starting point to the final point. So we take our final points, we take our initial points, subtract them from each other, then take our final time and initial time again, subtract them from each other, and then we'll be getting our v average. Now, what if I want to know the velocity at this particular point, this point here? At this point here, I want to know my velocity. Now, you can say that I'm not using the word average. Let's try to think of this like an exam in which 10 people write, let's say in mathematics. Now, the first person perhaps got 80, the second person 90, the third person 50, the fourth person 100, and so on and so forth till it gets to the 10th person. Now, if I were to find the average of the class, so let's assume that the average of the class is, say, 80%. Now, 80% is the average of the class. How do I arrive at this number? I simply added all the scores and divided it by the total number of people that wrote or participated in the test. Now, if I want to know the score of the first person, so remember we say, okay, maybe the first person got 80. So by right, 80 for the first person score matches our average. The second person, remember we said the second person got 90, but the average is telling us, oh, the average of the class is 80%. The third person 100, the fourth person different scores. So it means that average would never tell us the specifics of what is actually happening during the course of motion. Or like in this case, our test exam score, it will never tell us the specific score each student are having. But what if we want to know the specific score? Then definitely I have to talk about instantaneous. That's specific. That is at this point here, if I want to know what the person's score is at this point. Okay, so before we talk about instantaneous velocity, how then do we define average velocity? Remember, we've talked about the mathematical implication of average velocity. We said it simply means delta x over delta t. And if we hear delta over delta, it means slope of a secant line, also means the average rate of change. And so from our mathematical implication, we can define average velocity as simply the average rate of change of position with respect to time. Average rate of change of position with respect to time. Moving on to instantaneous velocity. So instantaneous velocity, we simply denote it mathematically or symbolically rather, denote it symbolically with V, then instantaneous IN. In some textbooks, you see ordinary V, like that is V standing alone. But for the sake of this video, we're going to be using V in. Then later on, we'll switch to V. When we talk about instantaneous, we just use the letter as it is. But for now, let's make do with this. So V in or V instantaneous will simply be equal to dx dt, derivative over derivative. Of course, when we hear the word derivative, what comes to our mind is calculus. Calculus. But notwithstanding, we'll talk about calculus much more later on because I know most of you have not been introduced to the concept of calculus. So, not to be scared, but just know that the x, the t, and the d here means derivative, and derivative over derivative. Again, just like what we said for average, so derivative over derivative, the first thing that wants to come to your mind is also slope, but this time around, slope of a tangent line. Slope of a tangent line. So that's the first thing that should come to your mind. Now, the second thing that should come to your mind is the instantaneous rate of change. So this time around, like the exam we said, so now I'm interested in what's the first person scored, what the second person scored, what the third person scored, what the fourth person scored, and what's the 10th person scored. So then I'm talking about specific. So when you are concerned about the specific, what is actually happening at this moment, at this point in time, now we're talking about instantaneous rate of change. So how do we define instantaneous velocity? We simply say it is the instantaneous rate of change of position with respect to time. The definitions are quite similar. For average, we say it is the average rate of change. For instantaneous, we say it is the instantaneous rate of change of position with respect to time. Now, quickly, let's come to our graph. Now, average, we're dealing with 2 points. That is, if this is x1, if this is xf. So, I want to find the average, just take the xf minus x1 divided by tf minus t1, or vice versa. But this time around, I want to get the velocity. What is actually happening? How fast am I moving at this point? So let me call this point, let's call it x, let me switch the number now. So let's say x3. At x3, what is actually happening? Or how fast am I moving? Now, if you want to solve this graphically, what we simply need to do, remember from our definition or from our analysis, we said it is the slope of a tangent line. So definitely, we want to draw a line that will touch this point at just one position. Remember, tangency means touching a particular shape or an object or a point at one point only. So we'll draw a tangent line in such a way that looks like this, that touches this point at just this location. So then we say this line is tangent. Then once we've done that, then we can find the slope of this line. The slope of this line will be our instantaneous velocity. The other way to solve for instantaneous velocity is by making use of calculus, where we differentiate. But for now, for the early part of this course, the way you solve for average velocity, instantaneous velocity, displacement, distance, acceleration will be through the use of your graph. That is your xt graph, your vt graph, and then your at graph. Instantaneous velocity also is measured in meter per seconds. All units of velocity is always in the meter per seconds. All right, so now that we're done talking about velocity, it's time to move to our second concept, which is speed. What is speed? All right, so before we talk about speed, let's quickly chip this in that velocity, whether instantaneous or average, can be positive, can be negative, or zero. So we talked about this when we talk about displacement, and then we said the signs simply account for the direction. Since it is in one dimension, if we have our object moving towards the right, then we say the average velocity or the instantaneous velocity will have a positive value, and we have our velocity heading towards the left, then we say to have a negative value. And then we set for velocity to be zero, either the object hasn't moved at all, or it moved and came back to the same exact position. So then displacement will be zero, and anything you divide by zero will simply be equal to zero. So also velocity is a vector quantity, that is, it has both magnitude and also direction. All right, moving on to speed proper. So like speed, we talk about the two types. The first one, the average speed, and then also the instantaneous speed. So average speed, we simply say it is the average rate of change in which an object covers distance. So we keep on using the word average rate of change because we're talking about average speed. So speed in general will simply be the rate of change at which an object covers a particular distance. Now, speed has no, or speed doesn't deal with direction. So it's the same analogy that you're looking at, what's it called? Maybe you're driving a car and then your eyes go to the speedometer. So that particular speed you say without caring about the direction in which you're traveling in is what we're trying to say. So the rate at which an object covers distance or a particular distance. So like we said for velocity, we have the average part. So the average speed will simply be denoted by SAV. And mathematically, this would be distance over time taken. So since this is average rate of change, again, delta over delta, that is the slope of our line. So this time around, I'm not considering the direction. Speed can never be negative. We'll always have a positive value or zero. Now, speed also is measured in meter per seconds, and speed is a scalar quantity. Speed is a scalar quantity. What's the difference between speed and velocity? So again, let's try to draw the motion in which we described, where we said a car is moving from this particular point towards this direction. Sorry about that. This direction, so moving like this. Okay, so this is my x initial, and then this is my x final. This is my t initial. This is my t final. Okay, so let's try and describe another car in this same motion. So this time around, the car is moving like this, then turns back, then goes like this. All right, so now we already said for this first one, for this motion, this one here, I'm pointing towards. So this one, when we use velocity to describe this, it doesn't really tell us, especially average velocity, it doesn't tell us what has happened in between this motion. So for instance, let's assume that this is the direction in which the car is traveling. You can see that there's a turning point here, or there's a turning back at this point and at this point. Yeah, that's a turning point. So velocity doesn't really care about that. So I will calculate for average velocity. Take our x initial or initial position, take our final position, subtract them from each other, divided by the time taken for both. But for speed tells us the rates at which we are covering distance. So everything that we said there, speed is going to tell us. So remember, speed, we say it is distance over time. And from our previous video, we didn't know how to find distance. Now this distance, we calculate distance from here to this point. We call it d1. The distance from here to this point, we call it d2. Then from this point here to this point, we call it d3. And then we take the total distance where we had d1, d2, and d3 and divided by the time taken. So we can find out how our object is moving in the particular motion that we're trying to describe. All right. Now, let's assume that we have an xt graph that looks like this. Okay. Again, we have a curve here. this is my x of position in meters. This is my t in seconds, t or time in seconds. Again, so let's assume that this is xi initial position, this is xf final position. If we're to be calculating for displacement, we know that at xi we have t high, at xf we have tf. Okay. If we're to be calculating for displacement, or displacement for average velocity, we will have taken xf minus xi divided by tf minus ti. But for distance now, we want to take, especially if it is a graph, we want to measure the distance that is along this path, the actual path taken by this object in this particular motion. So we take the distance and then we divide it by the time, no longer a straight line. But this time around, the slope of this curve is what we are going to use. So we'll talk more about this when we interpret our xt graph and then our vt graph. So we'll look at how we can find distance properly in one dimension. But this is just the concept. Now, moving on to instantaneous speed. Instantaneous speed, let's try and clear this. Instantaneous speed, there's no, what's it called? There's no refined definition, neither is there a mathematical implication for instantaneous speed. The only thing we can say about instantaneous speed is that, of course, we represent it with S in some textbooks, but for the sake of this video, I will write X and IN, S instantaneous. So we say instantaneous speed. Remember the example I cited when we're talking about speed? When your car is driving and then look at that particular moment, you look at your speedometer and then you're seeing a particular speed, whether 60 meters per second or 80 kilometers per hour or 120 miles per hour or any other unit that your car is using to measure speed. And that speed you're getting directly from the speedometer is your instantaneous speed, because it is that speed at that particular instant, that speed at that particular moment. But initially I said there's no mathematical implication and then there's no way to define or a proper refined definition of instantaneous speed. But the only thing we can do here is that anytime I have to find instantaneous speed, we solve for instantaneous velocity instead, and then we take the absolute value of our instantaneous velocity. I don't know whether this makes sense. What I'm saying is, let's come back to this graph. Let's say I want to find the speed at this point. Of course, you are driving a car and then you look at the speedometer. Well, I want to find the velocity at that point. Let's say I'm heading I'm heading northwards. I'm coming from the south, heading northwards. So if I check my speedometer and then I'm seeing something like 80 kilometers, still heading northward, then I'm talking about velocity. That is, talk about the magnitude, which is 80 kilometers per hour, and then the direction in which I'm going to, which is towards the north. But for speed, I only want to check the speedometer and get the speed only, get the magnitude. That is, when I look at my dashboard, I'm only seeing 80 kilometers per hour, and that accounts for my speed. So when we're asked to calculate for instantaneous speed, we calculate for instantaneous velocity instead. If this were to be a graph, draw a tangent line that touches this place or this position at one point, and then find the slope of this line. Remember, the slope you get here can be positive, can be negative. If it is positive, of course, that will be your instantaneous speed. If it is negative, you only take the the value, the positive value, and then that becomes your instantaneous speed. Instantaneous speed, again, also just like speed, is measured in meter per second. All right. Now let's move on to acceleration. So acceleration, we talk about three types: the average, the instantaneous, and then the constant. So what does it mean when we use acceleration to describe motion? Acceleration is simply the rate of change of velocity with respect to time. So how velocity is changing with respect to time. So let's say, for instance, you're in a car and then maybe you're moving at a constant speed. Perhaps the cruiser of the car is on. And then you notice that perhaps you get called, or you notice that there might be traffic, or maybe you have a sudden emergency and then you want to get to where you're going to faster than you would have if you're moving at that constant speed. So what do you want to do to the car? You want to increase its velocity. The concept or the process of increasing the velocity is what we refer to. Let me come again. So not just increasing, the process of changing the velocity, whether you increase or you decrease, is what we refer to as acceleration. That's why we say acceleration is simply the rate of change of velocity with respect to time. How velocity is changing with respect to time. Now for the first one, average acceleration, we denote it symbolically as A, then an AV as a subscript. And if we were to write the mathematical implication, we'll simply say delta V over delta T. Delta V over delta T. If we expand this, of course, this would be final velocity minus initial velocity divided by final time minus initial time. All right. Now, acceleration is a vector quantity. That is, in order to describe it efficiently, we must know our magnitude. We must also know its direction. So it's a vector quantity, and the unit is the meter per second squared. Now, average acceleration. What is its implication, or how do we define it? So we simply define average acceleration as the average rate of change of velocity with respect to time. With respect to time. So average rate of change of velocity is changing with respect to time. And this is the first implication we can get or analyze from our formula. Remember we said delta over delta would always mean the rate of change, the average rate of change. Now, the first one, the second one, from this formula I've written here, it looks like the slope of a line. But this time around, it has to be the slope of a VT line. When we're talking about velocity, we're concerned with an xt graph. So for acceleration, we're concerned when we take the slope at any 2 points, then definitely we want our graph to be a VT graph or a velocity time graph. So the slope of a line in a VT graph. So what we're saying is, let's say for instance, I'm given, let's try and make a much more familiar example. So the graphs that we mostly encounter something like this. So let's say I want to find if this is my origin, yes, which is 0.00. So let's assume that this is also my point 1. Let's assume that this is my point 1 and then this is my point 2. Now, if I were to find the graph or the acceleration between point 1 and 2, so what I simply need to do is to find the slope of this line. Remember, the slope of the line is constant. It doesn't really change. Now, but this graph would be A, V, and then C graph. For an xt graph, if you take the slope of the line, you are getting your average velocity, not average acceleration. All right. Now moving on to instantaneous acceleration. Moving on to instantaneous acceleration. But again, let's try to clear this place. Okay. For instantaneous acceleration, we simply say instantaneous acceleration symbolically will be represented. In some textbooks, they use ordinary A, but for the sake of this video, we want to use A in, and later on, when we talk about constant acceleration, we're going to do without the high n as a subscript. So A in will simply be dv over dt. Derivative over derivative. And now, when we hear derivative over derivative, it means number one, the slope of a tangent line, or also the instantaneous rate of change. Now, how do we define instantaneous acceleration? We will simply say it is the instantaneous rate of change of velocity with respect to time. The instantaneous rate of change of velocity with respect to time. Just like velocity, acceleration can be positive, can be negative, can be zero. Positive, negative, and also zero. When is acceleration positive? When I'm changing velocity towards the right. Remember, we said for velocity to be positive, it means I'm changing position towards the right. For acceleration, whether average, whether instantaneous, to be positive, it means you're changing velocity, your velocity is changing towards the right. If acceleration is negative, it means your change in velocity is towards the left. And for acceleration to be equal to zero, so the first instance, it means perhaps there's no motion, when the object is not moving at all. So the acceleration, the velocity, everything will be equal to zero. And then the second instant, if you are moving at a constant velocity, you are driving your cruiser is on, and then you feel no need to speed up or reduce your speed. You just want to move at a constant speed, like what Newton's first law described for us, an object in space. Moving with a constant velocity, we want to move like that for eternity. So that definitely will say that such object is not changing velocity, and the acceleration will be zero, because if the initial velocity and final velocity is equal or are equal, then definitely you are not accelerating. Velocity is not changing. All right, now moving to the final part of this video, constant acceleration. Constant acceleration. What does it mean for acceleration to be constant? The first thing we want to know is that constant acceleration simply refers to when acceleration has a constant value. So constant value could be could be, let's say, 10 meter per second squared, or it could be minus 9 meter per second squared. That's a constant value. But the question we want to ask ourselves, when acceleration is constant, are we talking about average acceleration or instantaneous acceleration? When acceleration is constant, are we talking about average acceleration or instantaneous acceleration? Now let's bring this example. Let's just break it down. So let's assume that we have 5 students, A, B, C, D, and E. A, B, C, D, and E represent students that we have. And these 5 students decide to write a test in physics with the overall score 100. And A were to get, let's say, 80. B were to have 90, C 95, D 85, E let's say 100. Now, if we are to find the average of this class, so permit me, I'm going to have to use a calculator. If we are to find the average of this class or of this test, so I would simply say 80 plus 90 plus 95 plus 95 plus 100 divided by 5. So let's quickly press that in my calculator. So we have 80 plus 90 plus 95 plus 95 plus 100. This is equal to 460. So 460 divided by 5. And 460 divided by 5 will give us 92. Now this is the first instant. Now remember, this just denotes average, right? Now if I want to know what A has scored, from the average I can't know, because the average is 92. It doesn't mean, in fact, you can see that neither of them got 92. So if I want to know the exact value of each of these guys, then definitely by calculating the average like this, I would never know that. But let's take another scenario. This time around, A, B, C, D, and E, perhaps the teacher was feeling kind, like, okay, since we have a lot of discrepancies in this course, let's try to retake the test. And this time around, hope you guys will perform better. And then they decide to write a new test. And this time around, A, B, C, and D all had the same grade. So let's say they had 100, for simplicity, 100, 100, 100, 100. Okay. So if I decide to take the average of this class, 100 plus 100 plus 100 plus 100 plus 100, that's 500 divided by 5. That will give me, so average is 100. Okay. Now, if I want to find out what the A score, right? Of course, I know A is 100. What the B score? B is 100. C 100. D 100. E also 100. Now, what is this telling me? When I have a constant value, when my acceleration rather is constant, then it means my average acceleration and also my instantaneous acceleration must be equal with what we've said here. Averagely, they had 100, and instantaneously or specifically, A had 100, B had 100, C had 100, D and E also had 100. So our first assumption is that my average acceleration and instantaneous acceleration must be equal for my acceleration to have a constant value. If that is true, then I can say, remember, average acceleration is given as AAV. Sorry, let me write this properly. AAV is given as delta V over delta T. I'm going to stop writing delta T for reason being that the reference point for time is always 0. That is, if the time were to be 12 o'clock now, of course, we're working with a 12-hour modulo, or some of you prefer to use a 24-hour modulo clock system. What it means is, if I ask you, maybe around 12, okay, let's say I'm working with a 24-hour modulo now. So 24 hours, maybe the time is 11 p.m. So that's around 23 o'clock. Then I'm like, okay, can you kindly meet me in 3 hours time? Because 3 hours time will simply be 2 o'clock in the morning, right? Because from 23, we have 0, and then we have 1 and 2, so making 3. But since the reference point for time is always 0, instead of having things like 26 hours, which is not possible, since we're counting in 24-hour modulo, then definitely we know that that's 11 becomes our reference point or our origin, and then we simply count 3 hours from that time, and it lands us on 2 o'clock in the morning. So if that is true, then I can write A average will simply be equals to delta V over T, because delta T and T still mean the same thing. Now my instantaneous acceleration, A, so now I'll stop writing instantaneous acceleration as AIN and just write ordinary A. So A again will simply be dV dt. We already said for acceleration to be constant, AAV and A must be equal, isn't it? So if I equate both equations, I can say A is equal to A average, and A average is simply A average is delta V over T. So if I were to expound this, delta V means V final minus V initial all over T. So cross multiply, we have AT is equal to V final minus V initial. So make V final the subject of the formula. We have VF is equal to V initial plus AT. And this gives us our first equation of motion. Remember, this equation How we arrive at this is by taking several assumptions. First of all, our acceleration is constant. And if our acceleration is constant, our average acceleration and instantaneous acceleration must be equal. And if we equate them, then we arrive at this final formula. Vf means final velocity. Vi means initial velocity. A means the constant acceleration. And T means the time taken during the course of that motion. All right, so we have about 3 different equations of motion. Of course, some textbooks you see 4, it doesn't really matter. So the fourth one is a special case. Now, how do we arrive at those equations of motion? So let's try and do that now. Okay, let me clear this area away. So let's say we have to have, this time around, we have to have an object moving in a plane with a velocity. So let's say this is v1. Again, let's say this is v2. Okay, so let me not use v2. Let's use what we are familiar with, so vi and vf. Now, if I were to find the average velocity in this particular motion, of course, it won't be possible because I know that v average, for me to get my average velocity average, I need my change in position or displacement. I need to divide it over time. But here, I'm giving v1, vf. And remember, for me to find average velocity, where I'm giving 2 velocities, and then of course these velocities have different times, and definitely I'll be looking for another concept, that is average acceleration. But what then do we do? How do we find average velocity in this scenario? So remember, change means v final minus v initial. But for this case, if I'm to find the average velocity, I simply want to add these 2 velocities together and divide it by 2. So I'll say v1 plus vf all over 2. Of course, if there were more, do v1 plus v2 plus v3 plus v4. Well, since we know that average velocity, we only require 2 points. So that's why we're using 2 points in this scenario. Now, originally from our equations of motion, we said vf is equal to v1 plus at. So I want to substitute what vf is into this equation here. And then, but before we do that, remember, we said this way is also our v average, another way to calculate average velocity, but only in a special case this time around. So when acceleration is constant. If acceleration is not constant, we can't find our average velocity in this way. For us to calculate average velocity, we always have to use delta x divided by t. But once acceleration is constant, we are free, and then we know 2 velocities. We are free to add them and divide it by 2. So that will also give us v average. Now, if this is straight, this is v average, this is v average. It means I can equate them just like we did in the previous video. So equating them, I can say delta x over t must be equal to v initial plus vf all over 2. Now I can substitute what vf is in this equation. So in order to derive our second equation of motion. So delta x over t will simply be equal to v1 plus v1 plus at all over 2. Now v1 plus v1, that simply gives us delta x over t equals to 2v1 plus at over 2. I can separate these quantities. Remember, for mathematics, when you have a plus b all over c, simply as saying a over c plus b over c. So that's what we want to do in this scenario. All right, so now I can say delta x over t is equal to 2v1 over 2 plus at over 2. So 2 cancel out 2. We have, so then after this, I want to multiply both sides by t. So multiply this by t. then multiply everything here also by t. So my final answer, t cancel out t, delta x will be equal to v1 times t, so that's v initial t plus, so bring this 2 forward, so we have 1 over 2, then at times t, that gives us at squared, and this gives us our second equation of motion. So let's write that here. So we know delta x, let's write that properly, delta x simply be equal to v1 plus, sorry, v1t plus 1 over 2 at squared, second equation of motion. Of course, if you're considering this an equation also, then you want to refine it, you can leave this as your equation where you multiply both sides by t. So this becomes v1 plus vf in the bracket of t over 2. So that's also an equation. This is an equation. So that's why we say we have, if you read some textbook and then you said you have 4 equations, that's fine. You have 5, you have 20, that's fine. So it just means you are making one quantity, this particular formula in this case. But standardly, we have just 3 equations of motion. So the third one, when we square this and then we equate it what we have here. So the third equation of motion will simply be equal to, so let me clear this part. Let's clear this also. And clearing this. So the third equation, we have squaring this, we have vf squared is equal to v1 squared plus 2a delta x. When we square this and then we make this disappear, you see the equation coming out from this, and then substitute it and we find our 3 equations of motion. Alright, so this is all I have for you for this video. Do well to like, share, and subscribe. In subsequent videos, we'll talk about the interpretation of vitigraph, xt-graph, and then how to solve practical applications of motion, which is free fall and then projectile motion. Bye bye.